Hi everyone, in this video we are going to learn how to actually write nuclear equations. Not reactions, equations, because we're going to learn how to write them down on pen and paper. But in order to do this we need to review isotopes, so hopefully you kind of remember what isotopes are. But basically they have that standard notation. So you have that Z is the big one, A is a little bit on the subscript, and then you have B as your superscript. So Z is just your element. Usually we use the symbol right there. So if we're talking about palladium, use PD. If you're talking about carbon, use C. We also have A. A is usually referred to as your atomic number. So now your atomic number is going to indicate your number of protons. Okay, so that's going to tell you how many protons are in the nucleus of this specific element. And then the last term we have up here is your superscript, and that is your mass number. Okay, and so usually when we talk about a mass number, we say it's the number of protons plus your number of neutrons. Okay, so we're going to add those two together. So hopefully this is all screaming right back to you. You already remember it. This is something that you hopefully didn't even forget. That would be ideal. But just in case you did, now we've brought that to the front of your mind. Now, in order to balance nuclear equations, you have to be so comfortable with that notation. And let me just give you an example of a nuclear equation so you can kind of see what I'm talking about. So this one that I'm about to write here is going to be where we take our uranium-235, which has an atomic number of 92. We hit it with a neutron. Okay, so that's your symbol for your neutron. And we break it apart into three different components. So you have your barium. Barium has an atomic number of 56. And so for this example, we have a mass number of 141. We're going to say that then it also creates krypton. So krypton is an atomic number of 36 with a mass number of 92. And then for this example, in order to balance out properly, we also need to create 3 neutrons, okay? This is a very, very, very standard nuclear equation. It's written on paper, so it's equation, not reaction. Very standard equation. But the most important thing here is that your superscripts and your subscripts have to cancel out. They have to be perfectly balanced. So let's start off by working with the top part, the superscripts, so we can kind of check this so you understand what I mean when I say balance out, okay? So on our reactant side, we have uranium-235. So we're going to add up all of our superscripts on the reactant side. So you have 235, then we have 1 neutron, and that must be equal to the sum of all the superscripts on the product side. So we have barium, so that's 141. We also have krypton, which is 92. And then we have 3 neutrons. So you multiply those together. 3 times 1, which really is just 3. That's pretty simple. But what we need to do now is say 235 plus 1 is actually equal to 236. And now we need to make sure 141 plus 92 plus 3 is equal to 236. And it absolutely is. So that balances out perfectly. We need to do the exact same thing with the subscripts. So same thing. Now we're just going with the subscripts. So for uranium-235, again, atomic numbers when we're using subscripts here. So we have 92 plus a neutron, which is 0. It doesn't have an atomic number. And that has to be equal to all the subscripts on our product side. So 56 plus 36 plus 3 times 0, right? That doesn't really do anything, but you have to account for it. And that gives us, so 92 plus 0, that gives me 92. Then you have 56 plus 36 plus 0. That definitely gives me 92, so this balances out perfectly, okay? So now what I'm going to have you do is actually practice one. It's going to be similar, but hopefully less complicated now that you've actually seen one go through. So what I would like you to do is actually to complete this nuclear equation. So we're going to start again with uranium-235. So that's 92. Again, we're going to treat it with a neutron. So nothing fancy here, but now this is where I need you to do something. So I'm going to ask you to determine what element A is. And I would also like you to determine what element B is. Okay, so B has a mass number of 97. And then we're going to say that we also have to create 1 neutron in order for this to balance out. So basically, what is A? What is B? Go. All right, did you get an answer? Hopefully you did. This was fairly easy because I didn't have you do any tricky stuff yet, but we will eventually. But basically, all you had to do was look at this atomic number down here. That's going to tell you exactly what that element is. So all you had to do is go to the periodic table, find the element that has the atomic number 52 or has 52 protons in its core, and you would find that A is element 52, which is actually tellurium. So you could also do the same thing for B. You had to go to the periodic table, find atomic number 40, and what you would see almost immediately is that element 40 is actually called zirconium. So now if I had also given you something like this, or maybe I gave you a couple pieces but left off one of these superscripts or subscripts, I would absolutely expect for you to be able to balance that out and actually figure out what numbers need to go where, what superscript should be, and what subscript should be. You need to be able to balance an equation. That's all I'm saying. Now, the big question is here. I see that I have a neutron on my reactant side and my neutron on my product side. So everybody who's ever taken a math class goes, oh, well, then that doesn't matter. Just cancel them out. Not true. With nuclear equations, you absolutely need to write out your neutrons. And the reason being is because we have these really cool things, but also super dangerous if they get in the hands of the wrong people. But you have these things called chain reactions. So think dominoes, all right? Chain reaction. So a chain reaction is essentially a reaction, a nuclear reaction usually, that causes another reaction to occur. Okay, and so like I said, think dominoes. So you've got one system here, you've got your uranium, let's just say that. You hit it with a neutron and then boom, it splits apart. And so we've got a krypton and a barium, but it also created 3 other neutrons. Well, those 3 other neutrons are like, well, they have so much energy. Think kindergartners after drinking a Red Bull, right? Okay, so they just go crazy and they just start smashing around, and those neutrons hit into other components that are also unstable. So the neutron hits the one thing, that splits apart, and then this neutron hits another thing, that splits apart, all while continuously generating more and more neutrons. So a chain reaction is simply where you have one thing here, you hit it with a neutron, and then all hell breaks loose. So it splits. Then you have over here, this splits, this splits, this splits. Just like with dominoes, you hit one, everything starts falling over. So the best way to visualize this is something here. You've got your uranium right here in the center. We're starting here on the side. So here's your neutron, here's your uranium. Your neutron hits the uranium and then it splits apart. And then you've created 1, 2, and 3 more neutrons. This hits another uranium, creating another neutron, and so on and so forth. And it just continues to go on and on and on. And so when you're trying to use this to facilitate energy and get actually nuclear power out of this, it's fantastic and it's perfect. When done safely, it's great. If this is ever done in the hands of somebody who might be creating maybe a dirty bomb or a nuclear bomb, super not a good thing. But usually the big problem is that terrorists cannot actually obtain what's considered a critical mass. So let's define that. Critical mass, right, is essentially the amount of fissionable fuel, love that word, fissionable fuel, to sustain a chain reaction. Okay, so just think about this. If you didn't have anything else in this box or wherever you're doing a reaction, you just have uranium and the neutron hits it, not much is going to happen. But if you hit your uranium with your neutron, but then you have a lot of other sources of fuel sitting in here, this reaction is going to be able to continuously just go on and continue over and over and over again. So the big issue is whether or not you have enough mass in there to sustain this reaction in a controllable manner inside a nuclear power plant so that you can continuously generate energy. And so the critical mass is the perfect amount of fuel that you need inside of your little reactor in order to have this process happen. Now with a dirty bomb, usually what happens is they have this completely not under control, and so they have this big explosion, all the mass leaves, and they're not able to contain it. And so what's a good thing, I guess, is that they are never able to get a very good critical mass. And so they always use all their fuel, all their source for an initial bang, and then that's it. So for us, we actually can do this in a controlled way, a safe way, and so we actually use our critical mass and the chain reactions in this beautiful, beautiful way. All right, so now the whole point of this video is to learn how to actually write a nuclear equation, so make sure you can do that. But I'm also going to sneak in a little bit of dimensional analysis. I apologize, but I just have to. So here's what you need to know. The critical mass of U-235, so everything we've been talking about today, is approximately 15 kilograms. I want to know how many pounds is that. Okay, so this is very simple, just reminding you to do some dimensional analysis. I'm even going to be nice to you. 1 kilogram is equal to 2.20462 pounds. All right, solve that for me. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. We have to brush those cobwebs off and get our brain back ready for some dimensional analysis. So all we had to do is use that simple conversion factor. So if we're starting with 15 kilograms, we know that for every 1 kilogram, we have 2.20462 pounds. That's it. We're trying to get for pounds. Our kilograms cancel out. 15 times approximately 2 is basically 30, but if you did this properly, you would come up with an answer of 33.0693 pounds. That's it. Hopefully you got that right. Take care of yourself. Have a great week and drink water.